So last time we talked about you proved the compactness theorem. So let me just remind you what it is. And it says that for every set of formulas sigma is satisfiable if and only if every finite sigma prime subset of sigma is satisfiable. And well, as far as I was told, you didn't finish the proof, right? No. And there's one step missing.
We are on the reduction proof, but we didn't finish it.
What?
We are on the structural induction, and we didn't finish it.
You didn't finish the structural induction.
Yeah,
so
just on the inductive step, like halfway through it.
Yeah. Okay. So the missing part of the inductive step, I'll give it to you as part of the next assignment. The next assignment, I'll post it tomorrow. And so rather than doing it here, I mean, conceptually, there's nothing very revolutionary there. It's similar to what we've seen. So they will be part of the next assignment. Okay? That's the missing step in the proof. So let us look, what I want to focus on today is some consequences of the compactness theorem. So let us first look at a lemma that I don't know if you proved it as part of the compactness theorem. So what about this claim? Have you shown it or not? I'm saying that for every sigma and every alpha, so sigma is a set of formulas and alpha is a formula. Sigma logically implies alpha if and only if some finite sigma prime subset of sigma, or say for some such finite sigma prime already logically implies alpha. So have you seen this claim? Yes. Right. And so you already proved this claim. Okay. And you proved it as part of the proof of the compactness theorem or before? Because it follows, anyway, if you prove it as part of the proof of compactness, there's no point of showing you that the compactness implies this. So, okay, so let us just move on. So what I want to talk today is about some other aspect of logic. And the other aspect of logic which is very important is the expressive power, the expressive power of logic. So I want to know what can we describe by a logic. So let me give you examples of what I mean by expressive powers. So what I mean is that we can draw two sets here. One is the set of all propositional formulas, say over some fixed, fixed set of variables. So say P1, P2, Pn, and so on. And the other is the set of all truth assignments to the same set of formulas, to the same set of variables. P1, P2, Pn, and so on. So in this set, I have assignments, truth assignments, infinite truth assignments because I have infinitely many propositional variables. And in this set, I have formulas. Now, if any of you, I mean, it's not something that you need to know, but if any of you has some background in set theory, can you tell me which of these two sets is bigger? First of all, note that each set is infinite, because if I look at the set of all propositional formulas and I have infinitely many variables, then I have infinitely many formulas. Just the atomic formulas are already infinitely many. And I also have infinitely many truth assignments, because I can take all the assignments that say Pi is true and all the other Pj's are false. I get infinitely many of those. So both of them are infinite sets, but one of them is a larger infinite set. We will talk about it in an extra, I mean, it will not be part of the curriculum of this course, but I will give an extra lecture about different sizes of infinity. Yes?
I think that first guy is bigger.
You think the first guy is bigger, the set of all formulas, right?
Yeah.
Right. And what do you think?
I think they're both very equal.
And we think are equal. So we just need one. So you just pick the, yeah, what do you say?
I think the right one is bigger.
The right one is bigger. Yeah, you can see it from the picture that the right one is bigger.
Yeah.
So it turns out that this is a small infinity, this is just countable, and this is a large infinity, this is uncountable. But we will talk about it. I'll give a special lecture on this notion. Yes?
Why the second set is non-countable?
Because the set of all, what is a truth assignment to all of those variables? A truth assignment, you can think of it, every truth assignment is a function. Every truth assignment is a function that goes from P1, P2, Pn, and so on, to the values true and false, right? So I can think of every truth assignment as an infinitely long binary vector. And the number of such infinitely long binary vectors is uncountable. It's a big infinity. Whereas here, every formula is just a finite combination of propositions. So this is only finite combinations over the variables, and these are, each of them is an infinite object. Each of them, each assignment needs to specify infinitely many entries if they are true or false. So this is a bigger infinity, but this is a smaller infinity. We will have a special lecture to discuss this. So what do I want to talk about? I want to talk about correspondence between sets of elements here and sets of elements here. So if I have a set of formulas here, so let's call it sigma, I can talk about the corresponding set of assignments here. Call it A of sigma. So what is A of sigma? It's the set of all V's, truth assignment V, such that V satisfies sigma. So if I have here a set of formulas, I can look at the corresponding set of truth assignment. The set of all truth assignment that satisfy the formulas in sigma. Okay? Let us look at an example. So say, here are some examples. So say sigma contains two formulas, P7 and not P7. What is going to be A of sigma? The set of all truth assignments that satisfy every element in sigma. What?
Empty set?
The empty set, right. So here I have the empty set. And what if sigma contains just the formula P1 or P2? That's all, one formula. What is going to be A of sigma? Yes.
All of them excluding ones where both P1 and P2 are false?
Right, right. So it's almost all of the formulas. So it's all assignments minus a single, minus the assignments minus the set of all V such that V of P1 equals false and V of P2 equals false. Right, so these are the only assignments that will not satisfy it, and all other assignments will satisfy it. Right? So let's work in the opposite direction. I'll tell you what is A of sigma, and you'll tell me what is sigma. So let's say A of sigma contains only one truth assignment, the assignment Vt. This is Vt is the all T assignment. So can you tell me what would be the corresponding sigma? So now I have a set of assignments that contains only one assignment, a single assignment. Yes?
Well, part of it would be all the variables or the propositional variables.
Right. So sigma will be just set of all propositional variables. So if sigma is the set P1, P2, Pn, all propositional variables, each of them is just a formula here. So I have infinitely many formulas, but the only way to satisfy all of them is to use this truth assignment, the one that assigns truth to all of them. So we have here a correspondence between sets of formulas and sets of assignments. So let us move on to, and the expressive power of the logic, we're going to talk about which set of formulas can be described this way. Let us look at a much more interesting set. So let us try, we are trying to use the logic to describe something which is outside the logic that comes from another domain. So do you all know what is what we call a graph in combinatorics? Right? A graph is a set of nodes and a set of edges between them. So I want to apply the logic to some different domain. So a graph, so G, V, E is a set of vertices V and a set of edges E, which is a subset of V cross V. So a graph is something like this. I have a set of edges and a set of vertices. So if I give them names, say A, B, C, D, E, in this case, V is going to be A, B, C, D, E. And the corresponding set of edges, I only have here, if it's an undirected graph, so I have here AC and dB. So let's talk about undirected graphs in which there is no direction to the edge. The edge is just a pair of vertices. And I don't care about the order. We can also talk about directed graphs when the order here matters. So I'll have to write AC and CA. But for simplicity, let us assume that our graphs are all undirected. Okay, so this is a graph. Have you all seen something like that? Graphs like that? So now we can ask about properties of graphs. Right, so we have all kinds of properties of a graph. When is a graph a clique?
Everything's connected.
What?
Everything else.
If
Everything's connected to everything else.
everything connects to everything else, right? So graph is a clique if the set of edges contains all possible pairs. Right, and a graph is called connected if you can walk on the graph from every node to every other node, you can find the path along the edges. Then we say that the graph is connected. So there are all kind of properties of graphs. Now I'm looking at a specific property, and this is colorability. So we say a graph coloring by k colors is a function, let's call it C for coloring, that goes from V to 1 to k such that for every x, y in which is an edge, C of x is different than C of y. So a coloring of a graph is an assignment of colors to the vertices in such a way that if two vertices are adjacent, they get different colors. It is very similar to like map coloring. We want to color maps, and we have states in the map, and we want to give different colors to two states that have a common border. So here I want to give different colors to two nodes that have an edge connecting them. So a coloring for this graph could be, I could color this graph by how many colors do I need to color this graph? What is the minimum number of colors that I need to color this graph? I can do it with 2. I can say this is going to be white, this is going to be black, this is going to be white, this is going to be black, and I got, and I need the coloring for E also. So let's call E white, and I have a coloring of all the edges with 2 colors, white and black, and no 2 adjacent vertices have the same color. Yes?
Do you need to color E just because it's not in a set of edges?
What? I need to color every edge, every vertex.
Every vertex.
It's a vertex coloring. So my coloring was assign white to A, B, and E, and black to D and C. Okay? So that's a legal coloring of a graph. So we can say that a graph so now we can talk about a graph is k-colorable if there exists a coloring of the graph with k colors. What? What do you say?
The Canadian spelling of color is different.
Ah, Canadian is with you?
Yeah.
Okay. Well, I'm just being lazy. Okay. So here is an example.
Spelling is better anyway.
No.
So here is an example. Here we had there a graph which is too colorable. Can you show me a graph which is not too colorable?
Single vertex.
Yes. What do you suggest?
Just anything that's three connected.
Three connected. A triangle is the simplest example, right?
Yeah.
This is not too colorable. And we can talk, I mean, if you have a clique of size k plus 1, then it's not k colorable. What? Yeah, and of course, you can have things which add without a clique, which is also, which are also without a clique of size 3, which will also not be 3 colorable. Okay. So we have the notion of a colorable. Now I say that we can kind of express it in propositional logic. So how can we express it in propositional logic? So given a graph V equals G equals VE, we can express its colorability with propositional logic as follows. So what we will do is we will have, let V be, so it is some set of, the set of edges, say V1 up to Vn. It can even be an infinite set, be the edges of the graph. So we will use formulas over P1 up to Pn. So we use the propositional variable for every vertex of the graph. So I have a propositional variable for every vertex of the graph. And now I want to write, that's now something I'm challenging you to find. So given our graph, and V is this set of variables, find a set of formulas sigma over P1 to Pn such that sigma is satisfiable if and only if G is too colorable. So we want to express the colorability by a set of formulas. So how are we going to do it? I want to write, so the idea is that I have here a propositional variable for every vertex of the graph. I can view T as one color and false as another color. So I want to write a set of formulas such that the colors T and F are a legal coloring of my graph. So you see what the trick is going to be? So instead of using colors, I'm going to use T and F. I already assigned the variable for every edge. So satisfiable means there exists a truth assignment that satisfies all the requirements. And the requirements that I'm going to write down are the requirements that say this is a legal coloring. So I'll write sigma of G to be, which formulas should I put here? To make sure that a truth assignment that satisfies this set corresponds to a legal coloring. Yes?
So for everything in E, you need like the first thing in E and not the second thing in that?
That they don't get the same truth assignment, right?
Yes.
So I need these formulas. For every edge, I'll write this formula P1 arrows not P2 and P2 arrows not P1. Oh, let's call them I and J. Pi arrows not Pj and Pj arrows not Pi, such that the pair ij belongs to edge. So I look at all edges, and for every edge I want to write my truth assignment. So here is an edge in the graph. This is Vi, Vi, Vj. This is Vi, this is Vj, and this is an edge in the graph. Now I want to make sure that my truth assignment doesn't give the two sides of an edge the same color. A color for me is true or false. So I want to say if this is true, then this is false. Right? And if this is true, then this is false. So that's what I wrote here. If the first one is true, then the second one must be false. If the second one is true, then the first one must be false. So this will be satisfied if and only if my truth assignment doesn't give the same value to those two edges. And if I collect those requirements for all the edges, then a truth assignment will satisfy this if and only if the truth assignment corresponds to a legal coloring. Yes?
What if both are false in this case? Wouldn't it be false implies true?
If both are false. Oh, wait. What?
I think we need an and with NOR.
Yeah, that's not like.
Okay. So I want to say Pi implies not Pj. That's a very good, that's definitely a bonus point. If both are false, then everybody is happy here because it looks like this. So what we need to say is Pi implies Pj and not Pi implies Pj. So now it says if I gets true, then Pj must get false. And if Pi gets false, then Pj must get true. So this ensures that they get different colors. Okay? So now we have the claim. Now we have the claim that says sigma for every graph G equals VE. G is too colorable if and only if the corresponding sigma G is satisfiable. Or in other words, if we go back to the picture that we started with, what we had here is we had a graph over variables. So here I have formulas. So given some G, which is the set of vertices is V1 up to Vn, and some set of edges. And here I have all formulas over V1 up to P1 up to Pn. And here I have all truth assignments to P1 to Pn. And I looked here at the set of all truth assignments that correspond to a legal coloring of G. All the truth assignments such that if I use T and F as colors, it's a legal coloring of G. And what we saw is that this corresponds to the set that we constructed here, sigma of G. So I wrote here a set of formulas such that assignment satisfies these formulas if and only if it is an assignment that corresponds to a legal coloring of the graph. Or in other words, the proof of this claim. So I have such a graph. I want to show that the graph is too colorable if and only if sigma G is satisfiable. But colorable means there exists a good coloring. Satisfiable means there exists a satisfying assignment. So, and if I want to say if and only if, so what I want to do is two directions. So if C is a legal two coloring of G, define V of C, a truth assignment, corresponding, I'm overusing V. So truth assignment T of C. T of C will give to Pi the following value. True if V of C, C of Vi equals, say, 1, and false if C of Vi equals 0. So again, I want to show you that the graph is too colorable if and only if this sigma G is satisfiable. So if you give me a coloring, I want to give you a satisfying assignment. And if you give me a satisfying assignment, I want to give you a coloring. So given a coloring, so I give you, you're given a legal coloring, right? A coloring, we said, is a function that goes from the vertices to the number 1s to k. In our case, it goes to the number not 0 and 1, but 0 and 1 and 2, from 1 to k. It doesn't matter. So I get a coloring, which is a function that assigns a number 1 or 2 to every vertex. And I want to define a truth assignment. The truth assignment will be if the number is 1, give it true. If the number is 2, give it false. I could switch. It wouldn't make a difference. And it's not difficult to see that if it is a legal coloring, no two adjacent vertices have the same coloring, then it satisfies each of those formulas. Because those formulas just say no two adjacent variables get the same value in the truth assignment. And what do I still need to prove in order to validate this claim? What is still missing? What is still missing there to validate the claim there? What do I need? Yes?
So the other direction?
The other direction. So the other direction, given a satisfying a truth assignment T that satisfies sigma G, define a coloring C of t as follows. How will I color a vertex vi? I will color it 1 if t of pi is true, and 2 if t of pi was false. And it's easy to say that if this was a legal, if this was a satisfying truth assignment, this will be a legal coloring. So if I have a truth assignment that satisfies these formulas, then I get a legal coloring. If I have a legal coloring, I have such a truth assignment. So the set of all truth assignments that correspond to a legal coloring of G is exactly the set of all truth assignments that satisfy this sigma G. So why are we? So we in some sense we've seen that we can express two colorability by a set of formulas, two colorability of a given graph. Why is it interesting? I mean, it's interesting in the sense of what can we do with propositional logic, but we also can get now a non-trivial result for graph colorings. It has nothing to do with logic. So as a corollary, I can get the following result, which just talks about graph coloring. So a corollary. So now consider infinite graphs. I can consider also graphs over infinite set of vertices. I claim that now we got the interesting corollary that a graph, any, for every graph G, including infinite graphs, so the set of vertices could be infinite. G is 2 colorable if and only if every finite subgraph of G is 2 colorable. So notice now we have something that doesn't mention logic at all. I give you an infinite graph, or if the graph is finite and this is saying nothing. If the graph is finite, then this is just repeating itself, because the graph is a finite subset of itself. But if I give you an infinite graph and I ask you, is it 2 colorable? It's the same thing as showing that every finite graph is 2 colorable, which is not at all not obvious. Because, you see, assume that I have an infinite graph that looks like this. So say my vertices are the natural numbers. 1, 2, 3, 4, 5. And now, so I have all the natural numbers. And now I have all kind of edges. So I can have an infinite graph defined over the natural numbers, and I can give you a rule which pairs of natural numbers are connected. Now I ask you, can you find a coloring of this graph with two colors such that you never get two edges with the same color, which are two vertices of the same color with an edge between them, right? And now this theorem says something about graphs. This will happen if you manage to color legally every finite subgraph. You don't have to worry about the full coloring of the full graph. And it's not the same thing, because maybe to color this graph, I'll use one coloring, and now to color this graph, I will have to change what I did here and use a different coloring. And to color the next graph, I'll have to change everything I did before again, and keep changing it each time to color the new graph. So how can I make sure that I have a single coloring that takes care of everything? And this sounds like the compactness theorem, and the compactness theorem does it for us. So by the fact that we can express colorability as a set of formulas, we get a compactness theorem for coloring graphs, which doesn't mention logic at all. Am I going too fast today, or it's okay? Okay, so let us prove this corollary, and then we'll talk some more about what can and cannot be expressed by sets of formulas. So the idea is as follows. You're given, I want to prove something about graphs. So proof of the corollary. I want to prove something about graphs. So what I'm going to do is given G, construct the set of formulas sigma G. And now, with this set of formulas, I have the following. So here I have the set of formulas sigma G, and I can have the statement sigma G is satisfiable. We know that this is if and only if G is too colorable. This is just what we have shown here. Given a graph G, we constructed a set of formulas that is satisfiable if and only if the graph is too colorable. Now, I can write here every finite sigma prime subset of sigma G is satisfiable. And I claim that this is equivalent. How do I know that this is equivalent? That sigma is satisfiable if and only if every finite subset is satisfiable. This is exactly the compactness theorem. So this is exactly the compactness theorem. Compactness theorem tells me if I have a set of formulas, it is satisfiable if and only if every finite subset is satisfiable. Now, all I need to show is that having every finite subset satisfiable corresponds to every finite G prime subset of G is too colorable. If I show this, then I showed you there is corollary about graphs. So this is, we already showed, this is by construction of sigma G. So the only thing I'm left to is showing the last equivalence. And then I'll get that these two things are if and only if. So, I mean, any questions up to this point? Yes?
Yeah, just one. Do we define subgraph as a subset of the vertices and all the edges, or just a subset of...
All right, so I didn't tell you exactly what is a subgraph. But a subgraph could just be a subset of the vertices and a subset of the edges. It's a subset of vertices and edges. But if the edges don't talk about the vertices here, then so yeah. So let me just put this comment here. So G prime equals V prime. E prime is a subgraph of G, which is VE, if this is just a definition, if V prime is a subset of V and E prime is a subset of E. So it is a graph, but the set of vertices is a subset of the vertices, and the set of edges is a subset of the edges. But being a graph means that all the edges here are between elements of V prime. So that's a subgraph. And that's a statement that I want to make here. Every finite subgraph is two-colorable. There was a question? Anybody wanted to ask a question? I think I saw.
I was just going to ask if E prime is a subset of E prime.
What?
I was just going to ask if E prime is a subset of E prime. But you had to.
No, yeah, so E prime is a subset of V prime times V prime.
Yeah.
Because these are edges in this graph, so they go between vertices of this graph. Okay? So now, all we need to show is this step. And this step, if we're given a so we are given we want to show that every finite sigma prime subset of CG is satisfiable if and only if every finite subgraph is two-colorable. So we need to show if and only if. So let me show. I always hesitate what is the right balance between doing things myself and leaving it for the assignment. So the advantage is that sometimes when I do things myself, it sounds repetitive and you kind of lose the thread of thought. If you think about yourself, you can see it. But sometimes thinking about it yourself is maybe a bit too difficult. So here we need an if and only if. Let me show you one direction and leave one direction for you for the assignment. Okay? So I will only show one direction. So let assume every finite sigma prime subset of sigma G is satisfiable. And let us show that every finite subgraph G prime of G is two-colorable. Right? Because I want to show that these two conditions are equivalent. So I'm showing you this direction. And I'm leaving the other direction for the assignment. Okay, so we are, so proof, given such G prime, which is V prime E prime, since E prime is a subset of E, we can look at the set sigma of G prime. Sigma of G prime is the set of all Pi, Pj get different colors, right? It's the set of all Pi arrows not Pj and not Pi arrows Pj, such that Vi, Vj belongs to E prime. So this is clearly sigma of G prime is a subset of the set of formulas sigma G, and is finite since G prime is finite. So by our assumption, it is one of those sigma primes. So by our assumption, sigma G prime is a finite sigma prime subset of sigma, is satisfiable, and therefore G prime is 2 colorable. Yes?
Do we need to make a distinction about the domain of propositional variables? Because we could have two G primes that have the same E prime but different sets of E prime. So does that make their sigma G prime different?
Again, what I didn't follow.
We could have two distinct subgraphs G prime such that their E primes are the same, but their V primes could be different. For example, one subgraph might be another subgraph with additional vertices, but none of the edges connecting to it. So do we treat their sigmas, respective sigmas, as being equal to each other, or are they different?
Right, so the respective sigmas, I see what you're saying. So let me just explain to all the class and then, okay. So he's raising a very good point, and he says, assume that I have two graphs. One graph is this one. I have an edge here, and this is V1, and this is V2. This is one graph, let's call it G1. And the other graph, G2, is the graph that has V1, V2, and also have here V3 and V4, V5, without any edges. Now, if I'm going to construct the set sigma of G for both of those graphs, sigma of G is a set that only involves formulas about edges. It says nothing about non-edges. So the sigma G that corresponds to this guy and the sigma G that corresponds to this guy will be the same sigma G. And somehow I kind of swept it under the rug. But it is still correct that if the graph is too colorable, it doesn't matter if this one is too colorable, if and only if this one is too colorable. And therefore, the fact that they have the same sigma G, so I'll have here G1 is too colorable if G2 is too colorable if this sigma G1 is satisfiable. So the fact that they got the same sigma g doesn't bother us because they will be colorable or not colorable together. But it's a good point to notice. Yeah. It's a very good point to notice. Yes?
What did you write after clearly sigma something what was that? Finite. What was after finite?
Finite subgraph. It's a finite subgraph G prime of G.
The last line. The last line.
Yeah, clearly EG prime, which is a subset of sigma G, and is finite.
And is finite.
And then there's one last thing after that.
What's after the comma?
Since G prime is finite.
Yeah.
Oh, this is since. This is the way I write since.
Yeah, sigma is fine.
It sings instead of sing, because it happens to me that I think of the next word I want to say and I start writing it too early. So I was thinking of the G here, so I put G already here. Sorry. Since G prime is finite. Yeah. I didn't know that anybody can follow my handwriting in the first place. But okay, so what we did, the gymnastics that we did now is just we showed that the propositional logic is already giving us some non-trivial results in other areas due to this notion of expressibility. I can express with a set of formulas being satisfiable, I can express the claim a graph is too colorable. I have a sigma that corresponds to all the graphs which are too colorable. So I can apply knowledge about the logic to obtain conclusions about graphs. Okay, so the remaining direction will be left as an exercise. So we wanted to show a statement about graphs. A graph is too colorable if and only if every finite subgraph is too colorable. We did it by just expressing two colorability as satisfiability of formulas. And here we can use the logic and saying sigma is satisfiable if and only if every finite subset of sigma is satisfiable. So every kind of property that you can express with satisfiability of set of formulas enjoys or suffers this kind of compactness property. So let us go back to this general discussion of, and I'll give you more examples like this in the assignment. Probably not in the exam, because my experience from previous runs of this course is that if I give you a story about some object and ask you to express it like this with formulas, it is almost an unfair question. I mean, anyway, so it will not be in the exam. The rate of success is too low. So let's go back to the general, but in the assignment I can allow myself to play with it. So let's go back to our notion of correspondence between set of formulas and set of assignments. So here I have all propositional formulas, say over some fixed P1, P2, Pn, and so on. And here I have all truth assignments to the same set of variables. And we talked about the notion of correspondence between subsets. So if I have here some set sigma of formulas, I match it with the set A sigma of all truth assignments satisfying sigma. And what we did now, we showed that if I want here all truth assignments that correspond to a legal coloring of a graph, I can write here a sigma that will be satisfiable if and only if you have a legal coloring. Okay? So now I want to discuss this a little bit more. We saw several examples, several positive examples of things that we could express. Now I want to talk about so for every sigma, I can define a sigma. It's a set of all truth assignments that satisfy it. But can I go the other direction? Is it true that for every set of truth assignments, I can find the corresponding sigma? You see what I'm asking here? If I give you a set of formulas, let's do it differently. I mean, set of formulas is a set of specifications. I want Pi to be equal Pj. I want Pj or Pi to be satisfied. So here I have a set of requirements, and here I have the set of all truth assignments that satisfy those requirements. And the question is, which sets can I describe with propositional requirements? Maybe there are things that I cannot describe with propositional requirements. Okay? If I want, so I want to show you a negative result, and the claim is that theorem sum subsets of truth assignments cannot be expressed as A of sigma for any sigma. There are some things, some sets of assignments that I cannot describe by a set of formulas. And we could have proved this theorem by just counting argument. We know that this set, we know, I said so, that this set is a bigger infinity than this set. Therefore, this set has more subset than this set. And since every set of formulas describes only one set of assignments, and I have more sets of assignments than set of formulas, there are inevitably some of those that do not have a description. It is kind of similar to this paradox that we saw in the first class. In the first class, we saw this paradox that said the set of all numbers that can be described with an English sentence of at most 100, 200 characters. And then we said, is there something you cannot describe? So here we look at the set of all sets of truth assignments that can be described by a set of formulas. And we say there are sets of truth assignments that cannot be. So by counting, if we know infinite set theory, we can prove it by counting. But I will show you concretely such sets without having to apply to infinite set theory. So for the proof, I have the following lemma. So consider for every I, let Vi be, Vi, I'm back to calling as truth assignments V because we are away now from the graphs. So it's not a vertex, it's a truth assignment. Vi be the truth assignment that Vi of Pj is true if j is less or equal I, and false otherwise, if j is greater than I. So let Vi be the truth assignment defined by this. So it's the truth assignment that gives you t, 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 up to the point I, and then gives false. So I can write them like this, like V0 is the truth assignment that gives false to everybody. V1 is the truth assignment that does true and then falsifies everything. Vn gives you n t's and then gives false everywhere. These are the truth assignments Vi. And I claim that this set of truth assignments cannot be described. There is no sigma that will describe this set of truth assignments. So the funny or kind of surprising claim is that there exists no set of propositional formulas sigma such that A of this sigma is going to be just the set of all the VI's I belongs to N. I cannot describe this set of truth assignments. We saw several examples of things that I can describe. Here is the negative result. I cannot describe this set. So is the claim clear? So I define some set here, this set of all the VI's. So here we have this set that contains V1, V2, Vn, all the VI's. This is my set A. And I claim that for every sigma, either what satisfies sigma is only a subset of these, or what satisfies either it doesn't take everybody, or it also takes things that should not be there. You cannot find a sigma such that those exactly will be the formula that satisfies sigma and no other. So is the claim clear? So what is the proof? The proof will be by way of contradiction. By way of contradiction, assume that sigma is a set of formulas satisfied by each VI. But every VI satisfies all these formulas. Right? I want to show you that it contains some things. It doesn't describe exactly this set. It's not going to work well. Okay? So now consider, let sigma prime be sigma union the following set of formulas: P1, P2, P3, Pn, and so on. So you give me a set of formula sigma. It's supposed to describe this set of assignments. I add formulas to it, all the PIs. Now I'm asking, is sigma prime satisfiable? Is sigma prime satisfiable? Is sigma prime satisfiable? So let me just say it more clearly. Assume by way of contradiction that sigma is a set of formulas satisfied by each vi and no other v. That's our contradiction. That this set sigma describes the set A sigma that we want. Now I'm asking, is sigma prime satisfiable? So we can easily see if I can satisfy all of sigma prime, I have to satisfy all of these guys. Which truth assignment satisfies all of these guys? They're all true. So if sigma prime is satisfiable, it must be satisfied by the all true assignment. Okay? So, if so, then Vt satisfies sigma prime. So, in particular, Vt satisfies sigma, since sigma is a subset of sigma prime. If I satisfy all of sigma prime, I satisfy sigma. What's bad with Vt satisfying sigma? Yes?
It's not part of the...
It's not part of the set, right? Because my set were all the formulas that give finitely many t's and then switch to f. And Vt is not one of these. But by our assumption, however, by our assumption on sigma, Vt should not satisfy it. So our conclusion, sigma prime is not satisfiable. Okay? I assumed that I had a good sigma. I extended it to sigma prime, and we concluded that sigma prime cannot be satisfiable. That's not a contradiction yet. This was by way of contradiction. I assume that I have such a sigma. How will I get the contradiction? I will show you, on the other hand, now let us show that our assumption implies that sigma prime is satisfiable. And now we will have a contradiction. See, by way of contradiction, I assume that I have a good sigma. Now I want to reach a contradiction. How will I reach a contradiction? I will show you that by our assumption, sigma prime is satisfiable. Now, how will I show this in 3 minutes? I don't even need the whole 3. We will apply the compactness theorem. What does the compactness theorem tell me? The compactness theorem tells me if I want to show to you that sigma prime is satisfiable, it suffices to show that every finite subset is. Right? So let me leave here on the board our VIs. So to show sigma prime is satisfiable, it suffices to show that every finite sigma prime prime subset of sigma prime is satisfiable. Yeah. Now, why will that be true? Because if I take here a finite subset, I take a finite subset here. This is my sigma prime prime. It's a finite subset. It contains only finitely many of the PIs. So how can I satisfy it? It contains only finitely many of the PIs. I will take one of those assignments here that gives true to all of the PIs in sigma prime prime. If I take a finite subset, it bites only a finite byte of this set here. So I have a VI, which is I is big enough so that everything that got into sigma prime gets true. So this will satisfy both sigma because it's one of the VIs, all the VIs fit as sigma, and it will satisfy all of these. So every finite subset is satisfiable. Therefore, by compactness, all of sigma prime is satisfiable, and we got a contradiction. So luckily or sadly or whatever, our time is over. But I will explain it again when we meet again on Tuesday.